Chapter 6, Section 3 is about conditions for parallelograms. So by the end of this lesson, you should be able to prove if a quadrilateral is a parallelogram. And we're kind of going backwards now. So far, you have learned to identify properties of a parallelogram. Now you will be given the properties of a quadrilateral and have to tell if it's a special case. Have to tell if it's a parallelogram. So here are 3 conditions that you need to memorize. So if one pair of opposite sides of a quadrilateral are parallel and congruent, then the quadrilateral has to be a parallelogram. So there's technically 2 things here. Opposite congruent sides, and they have to be parallel. So the arrows tell us they're parallel, the slashes tell us that they're congruent. If that's true, then it has to be a parallelogram. So if you have another quadrilateral, but you have 2 sets of congruent sides, then it has to be a parallelogram. And then if you have a quadrilateral and you have both sets of opposite angles being congruent, then you know it's also a parallelogram. So let's prove one of them. The first one we use a lot, so let's prove that. We're going to do 2-column proof, statements, reasons. There's a lot of them. So this time, remember, we're going backwards. I'm giving you some information and you're trying to prove that something's a parallelogram. So remember the definition of a parallelogram. It's quadrilateral, so it has 4 sides, or 2 pairs of opposite sides that are parallel to each other. So they tell us that KL is parallel to MJ, and they tell us that KL is congruent to MJ. So then let's see what else we have. Remember the fact that parallel lines means you're probably going to use one of our angle theorems. Why else would they tell us that? So if we treat this thing right here as our transversal, we know that angle 1 and angle 2 have to be congruent. Alternate interior angle theorem. And then we know that we have the reflexive property here with a shared side. So we already have that those 2 are congruent, and now we know that JL is congruent to JL. And then we can prove that we have those 2 triangles there that are congruent. That triangle KLJ is exactly the same thing as triangle MJL, and that's because of side, angle, side. Now because of that, erase all these markings here. You know, this is congruent to this. So remember, we're trying to go backwards here. I want to know that opposite sides are parallel. So far I have that these 2 sides are parallel, but I got to prove the other ones. So what I want to do is something with angles 3 and 4. So based on CPCTC, I know that angle 3 has to be congruent to angle 4 because they're a part of those 2 triangles. Now because of that, remember we can make this a transversal, and these lines here that cut through, I can use the converse of alternate interior angles to say that LM has to be parallel to KJ. So now that I know that, mark it in here, and by definition I know that JKLM is a parallelogram because I have 2 sets of parallel sides. So let's do a problem. Show that JKLM is a parallelogram for A equaling 3 and B equaling 9. So the first thing we're going to do is just plug stuff in and see what we get. If you plug in 3 here, 15 times 3 minus 11 gives us 34. And then plug in B here, so 5 times 9 plus 6, this is 45. Plus 6 more gives me 51. Plug in A again, gives me 30 plus 4 is 34. And then one more time, we're going to plug in 9. So 8 times 9 is 72. Take away 21 gives me 51. So remember, our goal here is that we're trying to prove that this is a parallelogram. So one of our stipulations said, if we go back here, if both pairs of opposite sides are congruent, then it has to be a parallelogram. So that's what we're going to use. Both pairs of opposite sides are congruent. This guy is congruent here, and this guy is congruent here. So we know that because both sides are congruent, JKLM is a parallelogram. So some more conditions. This next one's kind of confusing, but once you get it, it makes a lot of sense. It says if an angle of a quadrilateral is supplementary to both of its consecutive angles, then it has to be a parallelogram. So if I have this angle right here, and this angle is supplementary, and this angle is supplementary, then it has to be parallelogram. And then if the diagonals bisect each other, then it has to be a parallelogram. So these are kind of like the converses of all the theorems we learned yesterday. So if I know that this and this and this and this are congruent, that means Z is right in the middle of BD and right in the middle of AC. It has to be a parallelogram. So determine if each quadrilateral must be a parallelogram, and then justify your answer. So they give us some information here. They give us this angle right here, 73, and then they tell us that both of these are 107. Now what we want to check is that it's supplementary to this one and to this one. And if you add up 107 plus 73, you get 180. So we know that, yes, this is a parallelogram because this one right here, quadrilateral with angles supplementary to consecutive angles, is a parallelogram. So it's because of 6, 3, 4. Now the next one, all they tell us is that these two angles are congruent here. Now there's one of our conditions way back here that talks about angles, talks about opposite angles, but it says that you have to have both sets of opposite angles. This problem only gives us one. So no, we do not know that because we only have one set of opposite sides, or angles. One more problem. Parallelograms in the coordinate plane. So we need to show that this quadrilateral, JKLM, is a parallelogram by using the given definition or theorem. So let's plot these points on here. Over 2, up 3, 6, 2, 5, 0, and 1, 1. So this theorem that it talks about, 631, was way back here. That says if one pair of opposite sides are parallel and congruent, then the quadrilateral is a parallelogram. So when we go back to this, pick one pair of opposite sides, and it doesn't matter which ones you pick. Let's pick AD and BC. We need to prove two things with these. We need to prove that their slopes are the same, so that we can say that they're parallel, and we also need to prove that their lengths are the same. So let's talk about the parallel part. If I find the slope of AD, I'm going to go up 2 over 1. Up 2 over 1. And then if I find the slope of BC, I go up 2 over 1. So the slopes are the same, so that means the lines are parallel. So half of that definition is down. The other half of the definition says that we need to find the distance between the two, and we need to make sure that that's the same because we want their lengths to be congruent. So in order to do this, we can use the distance formula, which says that we need to do the difference of our x's squared plus the difference of our y's squared, and then take the square root. So let's do from A to D. If we plug in our points, we're using this one and this one, we'll do 1 minus 2 all squared, and then add 1 minus 3 all squared. This gives me the square root of negative 1 squared plus negative 2 squared, and that gives me 1 plus 4, or the square root of 5. So that's how long A to D is. So now I got to do the same thing, but for B to C. So these two here. So if I plug it in, I'm going to do 5 minus 6 all squared plus 0 minus 2 all squared. This gives me negative 1 squared again plus negative 2 squared again. Hopefully you can see that we're going to get 1 plus 4 or the square root of 5. So now I know that not only are they parallel, they're congruent as well. So that proves that this quadrilateral here, this four-shaped figure, is a parallelogram by definition. So you need to memorize these conditions for parallelograms, and that's how you're going to prove if something is a parallelogram. I wrote them all right here, nice and collected for you. You don't need to memorize the theorem numbers, but you should memorize what the theorems say. Make sure you write down any questions you have, and we can go over them in class tomorrow. Have a good night.